So hello everyone, this is lecture 4 for the thermal physics. In the last lecture we have completed the kinetic theory of gases, and today we will start the Maxwell Boltzmann velocity distribution. And before starting this, let me give you some two questions from the KTG. So a vessel contains 4 moles of oxygen and 2 moles of argon at absolute temperature T. The total internal energy of the given gas mixture is. So you need to find the total internal energy. So that will be the sum of individual gases. So for O2, this will be a diatomic gas, and for argon, it is a monatomic gas. So for the O2, the total internal energy is given by this formula F by 2 RT, that is degree of freedom here. So for the diatomic gases, it will be F transition will be 3, rotation will be 2, so total degree of freedom 5. So U will be given by 5 by 2 RT for the first gas, and this is for the 1 mole, and now the 4 mole of O2 will give you 2 to 4, 5 to 10 RT energy, and for the argon it is monatomic, so transitional freedom will be 3, only these are available, and it is F by 2 RT, so in place of F write 3, it will be 3 by 2 RT, and for 2 moles it will be 3 RT. Now total energy will be U1 plus U2, so that will be your 13 RT. So this option will be correct. Now there is one more question. 1 mole of an ideal gas having a specific heat ratio gamma, that is also called adiabatic index gamma, of 1.6 is mixed with 1 mole of another ideal gas having specific heat ratio of 1.4, so that is gamma 1 is 1.6, gamma 2 is 1.4. If Cp and Cv of the gas mixture, now there is a mix up of these two gases, and we need to find the relation between Cp and Cv of the mixture. So these are your options: Cv 2.08 R, Cp 2.9 R, Cv 1.48 Cv, Cp 1.52 Cv. So how can you find? So there you have two formulas, either way you can go. So first is this: you find Cv for the mixture, that is Cv1, Cv2, N1, N2, and Cv1 is related with the gamma as this R by gamma minus 1. So Cv1 will be equal to R upon gamma 1 minus 1, and Cv2 will be R upon gamma 2 minus 1, gamma 1, gamma 2 is given. Substitute here Cv1, Cv2, N1, N2 are 1 moles, so they are also given. So you can find the mixture Cv, and from there you can find Cp, that Cp will be Cv plus R. So you have Cp Cv, and Cp upon Cv is equal to that is this gamma, and that is your adiabatic index for the mixture. So you can find the relation, or you can use directly this formula: N1 plus N2 divided by gamma minus 1, N1 by gamma 1 minus 1, N2 by gamma 2 minus 1. So here gamma is a mixture of two gases, and this is for the individual gases, and this N1 and N2 represent the number of moles. So all are given. You can find the gamma from here, and Cp by Cv relation can you find it directly. So use either one. So let's move to the today's topic, that is Maxwell Boltzmann velocity distribution. So in this topic we will study about the general theory of this, and what is the velocity distribution actually. We will study that if there is some gas mixture, then there will be a large distribution of velocity from very small to very large velocity, and there will be large number of particles with different velocities. So studying them by the Maxwell Boltzmann distribution is called this Maxwell Boltzmann velocity distribution law. Now in this we will study the general theory of this, how can we derive the formula for the velocity distribution, and then we will study the 3D case, and in 3D we will study about the RMS velocity, most probable velocity, and the average velocity of the particles. Then we will go into the 2D, that how the expression changes for a 2D, means particle will be moving in the one plane only, 2D only. Then particle moving in 1D in the only one direction, that how velocity distribution vary for them. So we will study all the three cases. Then we will study some previous year questions and their solutions, and we will see some including additional question also. So let's see the general theory first. So from the KTG we already find the RMS velocity, that is under root 3 kT by m, and we can see that this RMS velocity depending on the temperature only. Now see, if temperature becomes constant, then we will say the Vrms will become constant. So if there is a large number of gas molecules, there will be RMS velocity, means if all the particles are moving inside this gas at the same velocity, that velocity will be Vrms. That is the meaning of root mean square velocity. So at particular temperature, if all gases molecules at certain temperature T moves at the same speed, then RMS value describes the velocity magnitude of all gas molecules. But we know that all particles are moving with different velocities, they are not at same, so there is a large distribution of velocities for the different particles. However, the speed of gas molecules vary widely, and it is necessary to determine the velocity distribution of the molecules. Now all particles are moving with different velocity, and there is a large distribution of velocity from very small to very large. So we need to study this distribution definitely. Now to study this, we need to take some assumptions. So we consider a volume of gas at constant temperature, some volume with constant temperature, where molecules are moving at different velocities. So this is a volume, and it is at temperature T, and all molecules are moving at different velocities, and the instantaneous velocity vector of each molecule is resolved into three mutually component Vx, Vy, Vz. Now each particle have some velocity v, and that velocity can be resolved in the Vx, Vy, Vz components for each particle. And if we take the velocity space now, means you have this velocity space Vx, Vy, Vz, then each particle will be represented by a point inside this, and this point represent the three resolved vectors of that velocity of that particle. Means in this velocity space you can represent the particle by a single point, and this point will represent the three velocities of, means three component of velocity of that particle. So now in this space we will study the velocity distribution. So now let us imagine a velocity space isotropic. What is the meaning of isotropic? Means it is same in all the directions. Whatever you are taking here, that will be same whatever you are taking here. So that is the isotropic mean. And now see, if all the particles, this is a sphere and this is a radius, constant radius. Now all the particles lying on this sphere will have the three different components, but net v square equal to vx square plus vy square plus vz square. So v square will remain same. Means net velocity of this particle, all the particles lying on this sphere will remain same, and all the particles lying on the second sphere will remain same. So that's how we'll study, and the particles lying on this sphere will have the same velocity, and means different spheres will give you different velocities. So that's how we're gonna study the complete different distribution with the help of these spheres in the velocity space. Now you will move from this sphere to this sphere, then there will be a change in the velocity, and that will be represented by dv, and this volume element will give you the change, that will be dvx, dvy, dvz. So we need to find the number of particles lying between this region, this annulus region, between two these spheres. So that region will give us the number of particles which are lying between v plus dv. So v and v plus dv, the number of particles lying in this will give us the, means that's how we can find the distribution if we can find between this. So let's see. So that the surface area of the sphere represent at any instant of time all molecules of equal velocities. So this is your surface. So this surface area will represent the total all the particles with the same velocity. Now the area, the surface area. Okay. Each molecule has a representative point in the velocity space, as I told you. Then this number of molecules with velocity lying between v and v plus dv would be represented by a spherical strip by of thickness dv, denoted by d and v. Now the number of vectors dvx, dvy, dz for each point inside this region between this and this will represent the total number of particles, and that will be this volume element, and we can represent it by d and v, and this will be a spherical strip. So each particle represented by a vector, as you can see. Now the particles between this and this bigger sphere will give you the total number of particles between v plus dv, and this will be denoted by d and v. Or we can say each velocity vector is defined by vx, vy, vz, and v square equal to vx square plus vy square plus vz square. So this condition will satisfy, means these three components can change for the sphere, but the net velocity will remain same for all the particles lying on the sphere. Now let's calculate this d and v. So how can we calculate the total number of particles? Means main motive here is to calculate the number of particles between this v and v plus dv region. So let's see how can we do that. That will give us the formula for the velocity distribution. So for an element volume in the volume space, velocity space, ds, dvx, dvy, dvz. So this will be the volume element for this complete annular region. The volume element will be dvx, dvy, dvz. So if we can find the density, then we can just multiply the volume and find the total number of particles. The number of velocity vectors which end in the elemental volume gives average number of molecules with velocity in between v plus dv. So whatever vectors lying in this region will give us the total number of particles. Now let d and vx represent the number of molecules whose s component of velocity lie between vx and vx plus dvx. So you have n number of molecules, and between means you have total dn. Okay, and now between means you have total n, and from this n you have d and vx whose component x component lying in this region, means vx plus v plus dvx, means all are n particles. So you have just find it those particles whose x component is lying in this region. So that is represented by d and vx, and these are lying between this. Now d and vx divided by total number of particles will give you the fraction of molecules with velocity component between vx plus dvx. This is the fraction, and we can write this is something like probability of finding the particle whose x component lying between vx and vx plus dvx. So this will be equal to, we assume this some probability function fvx dvx. This is an unknown function to be determined from the constant. So we need to find this function actually, and this is the probability function for the particle's speed. And similarly we can find for the vy component lying in the vy plus dy. So that will be given by this formula fvy, and for z it will be this. So we have these three equations. Now there are d and vx, those particles whose x component lying between that region. Now in that particles, in this d and vx, there may be some particles whose y component is also lying between this region. So from these particles we have found those particles whose y component is also lying, may have y component velocity between vy plus vdvy. Let this be represented by d square nvx vy. So this will give you the fraction d square nvx vy divided by nvx. So from this d and vx you have found these particles. So this is again the probability, and you can write it as dn vy n divided by n, or this equal to 1 upon n dn vx dn vy. Now from dn vx you can substitute the value of dn vx from here, that will be n fvx dvx. This will give you this. Now again you can take n vx vy, means from this vx vy there may be some particles whose z component is also lying between this region. So that will be represented by d3 nvx nvy vz, and that fraction will be written in this form d3, and from the vx vy you have written this, it will equal to dn vz divided by n. So this I am telling you to develop the concept, okay? You don't need to remember this whole proof, you just need to remember the result I will give you, but you must know how we came to this result. So d3 nvx represent the number of molecules whose velocity component would lies between, means this will represent your total particles who is lying between vx plus dvx, vy plus dvy, vz plus dvz. Now that's what you need, total number of particles lying between that region, v plus dv. So this will be by this, given by this n vz n, and this d3 will give you the total particles. This will be equal to 1 upon n dn vz d square nvx vy. So now in place of d square nvx vy you will substitute this value, this complete value, and this will give you the number of particles, that will be this. Now this n will cancel out, only one n is remaining. So these are your total number of particles which are lying between v and v plus dv, n fvx fvy fvz dvx dvy dvz. And if you divide this complete equation by dvx dy dvz, so this will give you the number density, that will be n fvx fvy fvz. So now you have find the formula, but you don't know what is fvx fvy fvz and what is this thing. So you need to find this value, only then you can just find, means you have the formula but you don't have the formula, that's the condition here. So let's find the values of these. Basically it represents the number of molecules lying in a small volume element dvx dvy dvz in velocity space. In velocity space, a velocity vector corresponding to a gas molecule represented by this as a point. So I already told you this point. Hence density of such points in velocity spaces. So density is given by number of particles per unit volume, will given by n fvx and fvy fvz. Now the molecule motion is isotropic, that is same in the all space. Velocity space is isotropic, that is means if space is isotropic, means wherever you are taking the measurement that will give you the same result. That means this density will remain same all over the space. So this density is constant, so d rho will be constant, that means d rho will be 0. So if something is constant, like some f function which is a depending on the independent variable, that is x y z, then df will be written as del f by del x dx plus del f by del y dy plus del f by del z dz. So same here we will write rho is a function of vx vy vz, so it will be del rho divided by del vx multiplied by dvx, and same del rho by del y del vy dvy, and all other will remain the constant for particular. So it will be del fvx divided by del vx dvx, and the fy fvz same del f vy divided by del vy dvy, and the remaining one. So this will give you 0. Now divide this complete equation by fvx fvy fvz, we get this equal to 0. This is equation 10, and see this equation 9 is valid, means only for those which have the same velocity is constant for them, because they are lying on the sphere. So v will remain same, x y z component may vary, vx vy vz component may vary, but the v will remain same. So v square equal to vx square plus vy square plus vz square. So this is a constraint condition lying on this for the particles. From here you can find that vx dvx vy dvy vz dvz will equal to 0, because this is constant. So this is your condition you will use to solve this. Now means this dvx, dy, dz are not independent, they are not mutually independent, can take any value but are subjected to 11. Means they can take any value but they must satisfy the condition that v remains constant. Now we will use this constant equation to solve this equation 10, to solve the equation 10. And how can we do that? We will use the Lagrange method. And what is the Lagrange method? So I will not go in detail, I will just tell you how we do this. So we use Lagrange method of undetermined multipliers. We multiply equation 11 with 2b and add to this 10 equation, this one. So multiplied with means add 2b to this and add to this, so we will get some independent variable then. So it will be equation 11 with 2b plus 10 will give you this 2b vx dvx, 2b vy dvy, and this. And now what happens, this vx vy vz, vx vy vz are now independent variables. So we can write means this coefficient of dvx, this coefficient of dvy, and this coefficient of dvz equal to 0. They must be equal to 0. So we put individually them 0. So to find, we are doing all of this to find the value of fvx, fvy, and fvz. So this is small f actually. So from here you just need to solve this differential equation by the separation of variable method. So how can we do this? Means you just take this to the negative side and take this del vx with the vx, and 1 upon f del f will give you integral, this will be log f, and here it will give you vx square by 2. So this will be of something this kind. Now log f will give you minus 2 v square by 2 plus log c, this is some constant of integration. This will give you f will equal to exponential this, and as you find for this, this will give you same for the vy and vz. So this is again a equation, this is 16. Now you know what is d and vx, that is d and vx divided by n equal to, we already find this. So this was this. So d and vy equal to n f vy dy, and d and v equal to n f vz dvz. So just substitute the value and you will get d and vx as nc, because this f vx, f vy, f vz will substitute here in place of this. It will be this, it will be this, and it will be this. Now see, we write it this from the 7. Now we know this formula d3, we have finded this, the total number of particles lying between v and v plus dv was this. So we need to substitute here fvx, fy, fvz. So we already find these values, so these are these. So substitute them. This will give you nc cube exponential minus b vx square plus vy square plus vz square dvx dy dvz. In place of this we will write v square, and this is dvx dy dvz. Now the density is this divided by dvx dy dvz, so this will be your density. Now see, you have finded the value. This is your density which remain constant because of the isotropic nature, and this is called the number density between v and v plus dv. This is the density between that region. So this is required Maxwell's velocity distribution function. Now when v equal to 0, this will give you nc cube, and when v tends to infinity, this will give you 0. Means number density when v tends to infinity, this will be 0. So now see, we have the equation, but see, we have some constant, that is b and c. We don't know the value. That's why this is again not the end of this struggle we are doing. So we need to find the value of b and c also. So let's see how can we find. So if we have this density and multiply with the volume, that will give you the total number of particles, but still we don't have b and c. So let's see how can we find. Now to determine the number of molecules in the velocity range v plus dv, what we did, an isotropic velocity distribution is considered. Molecules do not have any choice for preferred motion along particular direction. In such case, number of gas molecules in a given velocity interval can be easily evaluated. Now this is isotropic in nature, that's why we can easily calculate this by considering same everywhere. A spherical cell of radius v and v plus dv. Means how can we calculate? Means we have this spherical radius, and this is for v, and this radius is v plus dv for this. Now you just multiply the volume element dv from this and number density, and you will get the total number of particles. So you can use the simple symmetry because of the isotropic nature. Now what is the problem? Problem is then to find the number of velocity vectors that end in such a spherical cell, and this number is then equal to number of gas molecules with velocity v and v plus dv. Now to evaluate this number, we consider two spheres of radius v and v plus dv. As I told you, we consider these spheres. And the volume of the spherical cell, what is the volume of this annular region? So we can write it in two terms. We can write it in the Cartesian coordinate and the spherical coordinate. So in the Cartesian it will be dvx dy dvz, and this volume will be given by this complete volume minus this initial volume for this sphere. This is 4 upon 3 pi r is v plus dv, and this is v, so it will be 4 upon 3 pi r cube minus r cube. So this will give you, this term will neglected, this term will neglected, and this will cancel out. You will get 3v square dv. Now this is your volume element. If you multiply this with the density, this will give you a total number of particles. So multiply this with the density, nc cube exponential minus bv square. So when you multiply this, you will get this result. This is your total number of particles. So you have this result. Either you can find this using the Cartesian symmetry, but you can also use the spherical symmetry also. So in a spherical symmetry, dvx dy dvz is given by v square sin theta d theta d phi and dv, where theta goes from 0 to pi and phi goes from 0 to 2 pi. You must see my vector analysis lecture in the mathematical physics to understand everything about these vectors. They are needed for the exam. So this will be written this way in the spherical coordinates. Now we just put them, means we have volume element, multiply the density, will give you total particles. So density is this nc cube exponential minus bv square, and this is multiplied with this. d phi will give you 2 pi, and sin theta d theta will give you 2, that will give you 4 pi here, and this will remain same, nc cube, and this v square and dv, means all the term will remain same. You will just integrate these. So d and v will be given by this. So this is the same expression we get from here. Just multiply the density with this, and density is what? This is your density, multiply this term with this volume. This will give you total number of particles, which is same. So you can go either way. And now from here you can find the particle density, means particle fraction also. d and v divided by n will be given by this. So now we have the particle fraction, means these are the number of particles. These are the number of particles lying between region v and v plus dv. But still there is constants b and c, so we don't know the value of. So we need to find the constants. So evaluation of the constants c and b. So how can we do that? Now see what is the number of particles lying. That is this. We already find this value, that is equal to n, and this value. Now we know if we integrate for complete particle, that will give you n, means 0 to infinity. For all the velocity, that will give you total particle n. We integrate from 0 to infinity all the velocity, that will give you total number of particle n. So let's integrate, take this inside. Now this integral, you must remember this result for integration. X square exponential minus alpha x square dx will give you 1 upon 4 under root pi by alpha cube. So just compare this. In place of alpha we have b here, it will be 1 upon 4 under root pi by b cube, and this is equal to n. So from here you can find the relation between b and c. C will give you under root b upon pi. So now you have relation between c and b, but still both are unknown. So let's find the value of one and find the both of them. So let's see how can we do that. So let's find the root mean square speed, means the square of root mean square speed. So that will given by, means average of speed we need to find. So v square, and each particle, for each particle we will take this complete summation, means for the v1 square d first particle, v2 square for second particle, and divide by the total number of particles will give you the average value. So that's what we are doing, finding the average of v square. So this will be given by this formula. I hope you understood how we get this formula. Now we know what is d and v, the particles lying, which will be 4 pi nc cube. From the previous we can find this value. This is v square, and v square will give v4 here, and this d and v, this is the simple formula. Now here we will use this integral x4 exponential minus alpha x square ds. This will be given by 3 by 8 under root pi by alpha 5. So use this to solve this, and this will be in this form. So in place of b, whatever you have, write this. This will be 3 upon 8 under root pi by b5, and this will give you this 3 upon 2b. When you solve this, it will give you this. Now this is your speed, and from the kinetic theory of gases, you remember the result for the root mean square speed square, that will give you under root 3 kt by m, and the square will give you 3 kt by m. So this will be equal to this 3 upon 2b. From here b will be m upon 2 kt. Now you have the value of b, so c will be under root b upon pi, so c will be this. You have b and c now. So now you have everything you need. Now you have everything you need. Just substitute the b and c value in this, and this is your total number of particle fraction, or the total number of particle density. You can know everything by substituting c and b. So this will be your equation now. d and v over n equal to 4 pi m by 2 pi kt 3 by 2 v square exponential minus m v square 2 kt dv, fraction molecule with speed v plus vv. So this is the case for the 3D. Okay, so we are focusing mainly on 3D, but we will study 2D and 1D also. So this is your probability function actually. This is the probability function, number of particles lying between v and v plus dv divided by total number of particles. This is probability. So this is probability function. So this will give you the number of particles, the probability of finding the particles between the region V and V plus dV. Now, what conclusions or what interpretations we can do from this formula? So see, first, Fv depends on m. Now this probability function depending on the mass of the particle for particular fixed temperature, and the probability function is plotted for two different masses m1 and m2. Lighter molecules have broader speed distribution. If we plot this Fv with the velocity for two different gases, then we will get means for the lighter particles, if m2 is lighter, then we will get a broad curve, and for the heavy particle we get the small curve, means the shrinked curve, or the narrow, you can say. So, well, there is logic behind, we will see mathematical proof, but the logic is the particle is less in mass, then it can have the large number of particles with a higher velocity, so they will lie here somewhere, and total number of particles inside this curve will remain constant. I will prove that. And that means if large particle can have higher velocity, so that must curve will be go like this, broad here. And for the heavy particles, only few particles can have the higher velocity, so they will be narrow here, and that most particle will have the less velocity. So that was a logical reason. I will give you the mathematical proof later. Now second interpretation is f means probability function is depending on the square of the speed and exponential minus mv square by 2 kt. So probability will tends to 0 if v tends to 0. If v tends to 0, see probability function is tending to 0. And probability is tending to 0 when speed is tending to infinity. When the speed tending to infinity, then the probability of finding the particle will be 0. See, at minus infinity this will give you 1 upon infinity will give you 0. So this will be 0. In between Fv means what is the main now conclusion here, that particle will have some finite velocity in between this region, between the 0 and the higher velocity. That is the most probable speed. Actually, we will find this, what is the most probable speed. So what is the third conclusion? That is probability function. If you let's integrate this complete probability will be sum of all the probability must be 1. So let's see if the function is giving this not or not. If this must give us 1, means complete velocity from the 0 to infinity, the integration must give us 1. So let's see, dn by n 4 pi, and integrate this. So this will be the variables dv. Now use this result for the integration, x square exponential minus alpha x square. This will be this. Substitute here. Now see, 4 will cancel out, and pi 1 by 2 and pi 1 by 1 will give you pi 3 by 2, and you have pi 3 by 2 in the denominator. This will cancel out. 2 kt will cancel out this 2 kt, 3 by 2 and 3 by 2. So it means all will cancel out. You will get 1 here. So means f this probability function is a true probability distribution function. Okay, so that proves this. Now we can also check this, that the total particles, if you integrate for the whole velocity, the total particles must be n. So this take this n outside this integration we already did, that is 1. So it multiply with n, it will give you n. So total particle will always remain constant, that is n. So whatever variation you can do here, the total number of particles will remain same. That's why we are getting this narrow curve or the broader curve for different masses for different temperatures. So so n will remain constant, total number of particles will remain constant, that is n. As temperature increases, curve becomes flat and its peak value reduces. So what is the reason behind this? So logical reason we can see. So as temperature increases, then the particle velocity increases, means more particle will have the higher velocity. So that's why the curve will become broad here, and the maximum means this will reduce because most particles will shift to this side with the higher velocity. So this must reduce to make this n constant. Okay, so with the higher temperature this curve will go like this, and for the higher temperature this will become flat. So that's how you will get. So total area under this curve gives n. So total area will give you n because that represents the total number of particles, a constant quantity. Now see, you can also find somewhere, and if you get this capital F probability function, that is representing the dn by dv. So remember this term just in case you encounter with this. Now width of the curve. So how can we determine? Now the mathematical thing we have to see about the width of the curve. So see, when we study the step deviation on the the standard deviation, so that is the variance. So what the standard deviation represent? That will represent that to in which range the 68% of data is lying. Okay, so 68% of data is lying, that represented by the standard deviation sigma. So that's why the standard deviation represents the width of the curve. So let's find what is the standard deviation first. that will be given by the square average and the average square, means subtraction of this will give you the standard deviation in the velocity. So this will be your width of the curve. Now we know this is the RMS square, so it will be 3 kt by m, and this is your average speed square, that is 8 kt by m. So we know this is speed already. This is the average speed. So we will just study in the next lecture what is the average speed, most probable speed, and the RMS speed in detail. But now just remember the average speed is this. The square of average speed is this. So take the under root t by m common, this will be this. Now see this width or the standard deviation is proportional to under root t by m. So you have this, means the width is proportional to, directly proportional to temperature and inversely proportional to the mass. So as the t increases, width must increases. So as the temperature increasing, see this width is increasing. And I told you the logical reason that particles with the higher velocity are increasing. That's why this curve is shifting this side. And with the increasing mass, this must decrease. So with the increasing mass, for the higher mass you will get the narrow curve. For the lower mass, you will get the broader curve. And I told you the reason, because the small mass particles can have the higher velocity, more higher velocity. That's why this curve is broader for the lighter particles. So temperature increases, width increases, and curve shift downwards, area under curve and constant, because this and number of particles always remain constant. Only that's why this curve shifting we are here is taking place. So that is the reason behind. So that's all for today. I hope you understood everything now. So thank you everyone.